Hello class. So today in this video we're going to start on section 4.6. Now the theorems in this section, because it is going to be a little bit theorem heavy, they're going to be useful for us for some problems, but most importantly they're going to start to lay the groundwork for us getting into integral calculus. Okay, so that's going to be the goal as of now. We're going to start to work towards integral calculus. I think there's one more section where we do some limit techniques that now will allow us to compute limits more easily now that we know how to take derivatives. But the main goal right now is going to be, okay, now how can we get to the integral calculus part, which I haven't described exactly what it is, but we'll go through all the work. But you can think of integral calculus as kind of like going the opposite way as the differential calculus, and you'll see what that means when we get there. So today we're going to start with a simple theorem in the sense that when I draw it, you're going to see why it has to be true, right? So I won't actually prove it. You can always go to the book to see a proof. Okay, so just going to read it. It's called Roget's theorem. I don't exactly know how to pronounce it. I'm just going to say Roget's theorem or Rolle's theorem. Okay. So the key thing here is that there's going to be two assumptions that are going to continue on through all the theorems we see through this section. Okay, so these are going to be the two assumptions. Let f be continuous on a closed interval AB and differentiable on the open interval AB. Right? So those are going. So there's three assumptions here, but those first two are the ones that we're going to be seeing recurring all this section. Okay, so f continuous on the closed interval AB and differentiable on the open interval AB. Remember, for differentiability, we only do open intervals because the derivative is a two-sided limit. Right? With continuity, we did define one-sided continuity, so that's fine. For derivatives, we only work with open intervals. Okay? So f is continuous on the closed interval AB, differentiable on the open interval AB, and here's the extra assumption for Roget's theorem that f of A equals f of B. Okay? So given those three things, there has to be at least one input in the interval AB such that the derivative equals 0. So basically it's saying that there must be a critical point on this interval. Okay. So we could just memorize that and say, okay, if our function is continuous on the closed interval, differentiable on the open interval, okay, and f of A equals f of B, then there must be a critical point in that interval. Okay, so we could just memorize it, but I think just drawing it is the easiest way to see what's going on, like I mentioned. Okay, so we have a closed interval AB. We know that f of A equals f of B. So let's say this is f of A, this is f of B, and they're equal. So this is f of A, which equals f of B. Okay. Now we know our function has to be continuous and differentiable on this interval, so there's really only a couple ways we can draw it, right? We can't lift up our pencil, and we can't have any sharp edges or places where the slope is vertical. Right? So we could do some sort of picture like this. Okay, so oh, that looks like an edge. Sorry. Trying to draw it without any edges. Okay, something like that. There can be no edges. It has to be what we call smooth. So usually if a function is differentiable, so there's no edges or vertical slopes, then we usually call it smooth. And you can see here that it looks kind of smooth, right? Because there's no sharp edges. Okay, so let's say that's how our function f looks like. It's continuous and differentiable. Now, what this theorem is saying is, if you have something like this, then necessarily there must be a place where the derivative equals 0. So it looks like right about, it looks like right about there, the derivative should be close to 0. So let's just draw it there. Yeah, so let's say there, that's the tangent line of 0. That would be C. Right? So again, your function is continuous, differentiable, and f of A equals f of B. No matter how you draw it, you'll always be able to find a place where you can see, oh, the tangent line is actually 0 there. Like I drew here my tangent line. It seems to have slope 0. And that's what the theorem is saying. And then notice the way the tangent line looks like there. That means that the derivative equals 0. And it doesn't matter how you try to draw it. Okay, this is always going to be the case. No matter how you draw it, as long as these conditions are true, there will always be a place in that interval AB where the derivative equals 0. And that's all this theorem is saying. Now let's do a quick example. You're seeing how this applies. So let f of x be equal to sine of 2x on the interval 0 to pi over 2. Does Rogers' theorem apply to f? That's the first question. Second, if it does, on what interval? And then third, what x value satisfies this theorem? So what x value is there such that f prime of x equals 0? Okay. So let's start with the first question. Does Rogers' theorem apply to f? And remember, there's three things we have to check. F has to be continuous. F has to be continuous on the closed interval AB. Right, for Rogers' theorem. Second, f has to be differentiable on the open interval AB. And third, f of A has to equal to f of B. Right, so all these three conditions have to be satisfied by f in order for this to be true. Okay, so let's check the first one. So it doesn't hurt to start working with the largest interval we have. As of now, the largest interval we have is 0 pi over 2, because that's where our function is defined. So let's see if it works using that interval 0 pi over 2, so 1. So f sine of 2x, we know that the sine function is continuous everywhere. So for sure, it's continuous on the interval 0 pi over 2. So the first part is satisfied. F is continuous on the interval 0 to pi over 2. Okay. Now, is the function f differentiable on AB? And I remember this, all this is saying is differentiable means whether the derivative exists. So if you can find the derivative on this interval, then it exists. Right? Now, what's the derivative of sine of 2x? Well, you would have to use the chain rule here, right? Because you have a composition, you have sine, and inside sine, there's the function 2x. So what would be the derivative? It would be the derivative of the outside. The derivative of sine is cosine. Leave the inside the same. So leave it as 2x, multiplied by the derivative of the inside, which is 2. That function, which is the derivative, exists everywhere. So for sure, it exists on the interval 0 pi over 2. So it's differentiable there. Right, so f is differentiable on 0 pi over 2. Again, for derivatives, always work with open intervals. Now, the third thing we have to check is, does f of a equals f of b? So is our function equal on the endpoints? Okay, so let's go ahead and check. So let's see what f of 0 is. So f of 0 is plug in 0 for x, so sine of 2 times 0, which is sine of 0. If you don't remember your unit circle, this is just 0. Okay. So that's one endpoint. Let's see whether f of b or f of pi over 2 is also 0. So remember, the endpoints have to be equal. F of pi over 2 is sine of 2 times pi over 2. Simplifies to sine of pi. And again, if you don't remember your unit circle, that's fine. It's also equal to 0. So f of 0 equals f of pi over 2. So we're good. The endpoints evaluated in the function are equal. So f of 0 equals f of pi over 2. So yes, Rogers' theorem does apply. And on what interval? Well, we can just take the largest interval, which is 0 pi over 2. So Rogers' theorem applies to f on, again, just take the largest interval, so 0 pi over 2. Okay. Now let's answer the last part. What x value satisfies this? Okay. Now there might be more than one x value that satisfies this. Basically, all our theorem is saying is that there must exist at least one. Yeah, so if you read it, then there is at least one input in that interval such that f prime of z equals 0. So when we go here and actually try to find, okay, now we know that such at least one input must exist on the interval 0 pi over 2, such that f prime of that input equals 0, we can actually go ahead and find it, right? Because we know it exists. Okay, so we can ask for what x values in the open intervals. Remember, we don't count the endpoints. So 0 pi over 2 does f prime of x equals 0. So we can go ahead and check. So we already know what f prime is. We found that in the previous part. F prime was equal to 2 cosine of 2x. And you can just go ahead and solve this. Okay. So set it equal to 0. Again, by Rorschach's theorem, there must at least be one solution to this equation, to 2 cosine of 2x equals 0. There must at least be one. We're guaranteed that this is the case by Rorschach's theorem. And we can go ahead and find it. We can divide both sides by 2. So we're actually just solving cosine 2x equals 0. And then we did this in the first homework, but I'll go ahead and do it again just as a summary. Whenever you're trying to solve a trig equation like this, trig expression equals 0, and the input is not just x, then you just have to do a simple u substitution. So what you want to do is you want to let u be equal to 2x, and then solve cosine of u equals 0. So this we should know, and again, this just comes from the unit circle. If you don't remember, that's fine. But when is u equal to cosine of u equal to 0? Well, u has to be any multiple of pi over 2. Let me use k times pi over 2, where k is any integer. Actually, let me not use set notation. Use k is any integer. So this is just saying multiples of pi over 2. So for example, 1 times pi over 2, 0 times, oh wait, but 0 doesn't work. Yeah, so so it's actually not every multiple. So let me be careful here. So pi over 2, then 3 pi over 2. Okay, so it's actually pi over 2 plus multiples of pi. Yeah, so this is actually the correct. So see, it's useful if you remember what the unit circle is. Okay. So what does this mean? K is any integers. For example, u can be pi over 2 plus 0 times pi. So it's pi over 2. Cosine of pi over 2 is 0. We can let k be 1. Then we have pi over 2 plus pi. That's 3 pi over 2. Cosine of pi over 3 pi over 2 equals 0, and etc. If you start with pi over 2 and add multiples of k pi, k can be negative, can be positive, can be 0. As long as it's an integer, that's all the solutions for this equation. Now, to go back to the original equation, you just plug in what u was. K pi implies we divide everything by 2 to find what the original x is. Let's get pi over 4 plus k times multiples of pi over 2. Now, whichever of these lie in the interval 0 pi over 2, those are going to be the answers. Right? So how many of them lie there? Well, it seems just 1. It appears to me when k equals 0. So implies when k equals 0, x is pi over 4. That's inside the interval. And x equals pi over 4 satisfies, just by the work we showed, that the f prime of pi over 4 equals 0. And again, this has to be the only one, because if k is negative 1, for example, pi over 4 minus pi over 2, that's less than 0. If k is 1, pi over 4 plus pi over 2, that's greater than pi over 2. And of course, if we make k larger, it's either going to be larger in the positive direction or larger in the negative direction. So this is the only solution. And again, this solution was guaranteed by Rorschach's theorem. There's at least one.